Welcome to White Space. Can a black hole really get kicked out of its own galaxy? Put this on in the background. Close your eyes if you want and let the story carry you. There are places in the universe where the known rules of physics simply stop working. Not bend, not stretch, stop. These are regions where matter has collapsed into an object so dense, so gravitationally extreme that not even light moving at 300,000 kilometers per second can pull itself free. We call them black holes. And for most of human history, they existed only as equations. A consequence of mathematics that even the people who wrote those equations refused to fully believe. Today, we believe. More than that, today we observe, measure and study these objects with instruments their discoverers could never have imagined. And what we find every single time is that reality is stranger than the theory predicted. Black holes do not simply sit in space and consume. They spin, they merge, they wander, they steal, they hide, they scream in frequencies no human ear can register across hundreds of thousands of light years. They are not passive objects waiting for material to fall in. They are active, dynamic, sometimes violent engines at the heart of galaxies, including our own. This is a journey into the most extreme environments the universe has produced. What black holes are, how they behave, what they do to the space and time around them, and why the largest ones challenge everything we think we understand about how massive an object can become. We begin not with the center of a black hole, but with its edge. Every black hole is defined by a boundary, a surface, not physical, not made of any material, but a threshold beyond which the rules change permanently. This boundary is called the event horizon. Cross it, and the geometry of space-time itself redirects everything. Every path, every trajectory, every photon toward the center. There is no escape vector, there is no direction that leads outward. Every road leads in. Inside the event horizon, the concept of away from the center ceases to exist as a spatial direction, it becomes a temporal one. Moving toward the center is as inevitable and as unstoppable as time moving forward. The singularity is not a place you travel to. It is a moment you arrive at. At the center lies the singularity, the point where all the mass of the original collapsed object has been compressed into effectively zero volume. The mathematics here produce infinities, infinite density, infinite curvature of space-time. And infinities in equations are almost always the signal that the theory has been pushed past its limits, that the model has broken down, and something more fundamental is needed. General relativity describes the singularity with precision up to a boundary it cannot cross. Quantum mechanics, the other great pillar of modern physics, governs behavior at vanishingly small scales, but it has no satisfactory way to incorporate gravity at the singularity. Both frameworks fail simultaneously. What actually happens there remains genuinely unknown between the event horizon and the singularity. Some black holes contain a second boundary, an inner horizon. This inner structure is particularly associated with rotating black holes, and rotation, it turns out, is one of the most important properties a black hole can have. Consider what happens when a massive star runs out of fuel. For millions of years, nuclear fusion in the core has been generating outward pressure, the force that holds the star up against its own gravity. When that fuel is gone, the outward pressure vanishes. Gravity wins instantly and completely. The outer layers of the star collapse inward at a significant fraction of the speed of light. The core is compressed into an almost impossibly small volume. And here is the key: the star was already spinning. As the collapse shrinks its radius from millions of kilometers to just a few. The conservation of angular momentum, the same principle that makes a spinning figure skater accelerate when they pull in their arms, causes the rotation rate to increase by an enormous factor. The resulting black hole spins not slowly, not gently. in some cases at rates approaching the absolute physical limit. That limit is set by the speed of light. A black hole cannot rotate its event horizon faster than the speed of light at the equator. Any faster and the event horizon would dissolve. The singularity would become, in the language of physics, naked. A singularity exposed to the rest of the universe, unshielded by a horizon. Most physicists believe this cannot happen, that nature always finds a way to prevent it. The principle is called cosmic censorship, and while it has never been formally proven, observations consistently seem to support it. The black hole at the center of the galaxy NGC 1365, located about 60 million light-years away, has been measured spinning at approximately 84% of this maximum possible rate. Its diameter exceeds 3 million kilometers, its mass equals several million suns, and as it rotates, it does something remarkable. It drags space-time along with it. This is called frame dragging. It is a direct prediction of Einstein's general relativity, published in 1915, and it took nearly a century to confirm observationally. The idea is that rotating mass does not merely sit in space-time, it grabs it, twists it, pulls it into rotation along with the mass itself. The region where this effect dominates, just outside the event horizon of a rotating black hole, is called the ergosphere. Objects inside the ergosphere cannot remain stationary relative to distant observers. They are forced to co-rotate with the black hole, no matter what. This region is not just a curiosity. The ergosphere is a location where, in principle, energy can be extracted from the black hole itself, extracted from its rotation. A process proposed by mathematician Roger Penrose and known as the Penrose process. A particle entering the ergosphere can split into two fragments, with one fragment falling into the event horizon in a specific way that causes the black hole to lose a tiny amount of rotational energy, while the other fragment escapes with more energy than the original particle carried. The black hole's spin decreases ever so slightly. The escaping particle carries away the difference. This is not theoretical speculation. It is one of the candidate mechanisms for how black holes can drive the most powerful jets of energy in the known universe. 8,000 light-years away, in the constellation Cygnus, sits a system designated V404 Cygni. It consists of two objects in close orbit, a black hole roughly 9 times the mass of the Sun, and a companion star, a red giant. The black hole is slowly consuming its companion, pulling material from the giant's outer atmosphere into a rotating disk of superheated plasma. This disk, called an accretion disk, is one of the brightest environments in the galaxy when the system is active. But what makes V404 Cygni particularly unusual is what its jets do. Relativistic jets, concentrated beams of plasma and radiation fired from the poles of the black hole, are a common feature of accreting black holes. What is not common is for those jets to swing their direction noticeably within seconds. Astronomers observed V404 Cygni changing the orientation of its jets on timescales of minutes. Over the course of observations, the jets swept across a wide arc. This behavior was traced back to a misalignment between the black hole's spin axis and the plane of the accretion disk. The inner part of the disk, close to the black hole, is being dragged around by the frame dragging effect. It precesses, tilts, wobbles like a gyroscope, slowly losing its orientation. And as the inner disk wobbles, the jets follow, they sweep, they arc, they point momentarily in almost every direction before continuing their oscillation. The accretion disk in this system spans roughly 10 million kilometers. Its inner edge is deformed by a few thousand kilometers, a tiny fraction of the total size, but enough. The black hole's gravity grabs that deformation and carries it around. And the result is a sprinkler that never stops turning. Not all black holes are embedded in companion systems patiently feeding from a partner star. Some become isolated, and some, against all expectation, leave their host galaxies entirely. About 8 billion light-years from Earth, in a direction we associate with the constellation Leo, sits an object called Quasar 3C186. A quasar is the name given to the intensely luminous core of a distant galaxy, powered by a supermassive black hole, consuming enormous amounts of material. The black hole at the heart of 3C186 has a mass approximately equal to 1 billion times the mass of our Sun. What makes 3C186 extraordinary is that it is not sitting quietly at the center of its host galaxy. It is moving away from that center at roughly 7.5 million kilometers per hour. Moving so fast that, given enough time, it will leave the galaxy entirely, becoming a rogue quasar, a supermassive black hole wandering the intergalactic void, dragging its gas cloud with it. How does something the mass of 1 billion suns get kicked out of a galaxy? The leading explanation involves gravitational waves. Gravitational waves are ripples in space-time, produced whenever massive objects accelerate. The most powerful gravitational waves we have detected were produced by merging pairs of black holes. When two supermassive black holes merge, a process that can take millions of years as the pair gradually spirals inward, they emit gravitational waves. If those waves are emitted asymmetrically, as happens when the two merging black holes have different masses or spins, the resulting gravitational wave emission is stronger in one direction than another. By Newton's third law, the merged remnant receives a kick in the opposite direction. In the case of 3C186, that kick was powerful enough to overcome the gravitational binding of an entire galaxy. The merger of two supermassive black holes released a gravitational wave recoil comparable in energy to the simultaneous detonation of hundreds of millions of supernovae, and the result went flying. The merger of black holes is not rare. Evidence now suggests it is one of the primary mechanisms by which the largest black holes in the universe grew to their current size. Consider the problem of the most massive black holes we observe. Some have masses measured in tens of billions of solar masses. The most straightforward way to grow a black hole, accreting gas and dust from its surroundings, is an extraordinarily slow process relative to the age of the universe. To build a black hole of tens of billions of solar masses purely through accretion would require conditions that stretch credibility. The alternative, or more likely the complement, is mergers. Black holes in dense stellar environments or at the centers of colliding galaxies can find and consume one another. Smaller black holes in the orbit of a larger one can spiral inward over time, losing orbital energy to gravitational wave emission, and eventually merge with the central object. The large black hole grows. The small ones disappear. Repeat this process over cosmic time across many mergers, and the path to billion solar mass black holes becomes more tractable. Observations support this picture. The most massive galaxies in the universe, galaxy clusters, the largest gravitationally bound structures in existence, host black holes that seem far too large to have grown from a single collapse event. The kinematic signatures of the stars orbiting these black holes point to histories of repeated mergers, of galaxies absorbed into galaxies, of black holes consumed by black holes. Gravity is patient. It has had over 13 billion years to work. In some environments, the relationship between black holes operates less like a merger and more like theft. Gravitational wave observatories have detected the merger signals of black holes with masses that did not fit easy expectations. In one case, two merging black holes both had masses exceeding 20 solar masses, heavier than standard stellar evolution models predicted they should be. Analysis of the signal pointed toward an unusual explanation. The two black holes had grown larger than expected, not from star formation alone, but from stealing material that had originally been destined for a nearby, much more massive central black hole. Before they became black holes, the progenitors were massive stars orbiting close to a galactic center. As they evolved and eventually collapsed, the resulting black holes continued orbiting the central supermassive black hole. But in doing so, they passed through the accretion flow. The gas and dust spiraling inward toward the central monster was intercepted, skimmed, stolen. The smaller black holes fed parasitically from the larger one's food supply. They grew heavier than their stellar origins alone would have produced. Then, eventually, they spiraled together and merged, their collision sending gravitational waves across 800 million light-years of space to be detected in instruments on Earth. Theft, merger, signal detection, the universe leaves records of its own history written in the geometry of space-time itself. There is a structure around many accreting black holes that serves as a physical record of galactic history in a different way. It is called the torus, a dense, roughly donut-shaped ring of gas, dust, and molecular clouds that surrounds the central engine at a distance, hot and turbulent at its inner edge, where radiation from the accretion disk hammers it, cooler and denser, toward the outer regions. The Atacama Large Millimeter Array, a network of radio telescopes in the Chilean desert operating in concert as a single instrument of extraordinary sensitivity, has been used to resolve the structure of this story around black holes tens of millions of light-years away. In one case, the observations measured a torus approximately 20 light-years across, a structure of remarkable extent for material so close, in galactic terms, to a black hole. What the torus reveals depends on its shape. A symmetric, smoothly distributed torus suggests a black hole that has been accreting quietly and steadily in an undisturbed galaxy. An asymmetric torus, one side denser than the other with irregularities in its distribution, carries the imprint of past disruption. The most likely source of that disruption is a galactic merger. When two galaxies collide and eventually merge, the gas reservoirs of both galaxies are disturbed. Shock waves propagate through the interstellar medium. Material is redistributed. Some falls toward the central black hole, feeding it. The rest settles into a torus that retains, for billions of years afterward, the memory of what happened. Reading the shape of a torus is reading the history of a galaxy. The relationship between black holes and the galaxies they inhabit is not one-directional. A black hole does not simply sit passively consuming what comes near it, leaving the rest of the galaxy untouched. It responds to its environment, and it shapes that environment in return. The mechanism of that shaping is energy output. When a black hole accretes material efficiently, it converts a fraction of that material's mass into pure energy, a conversion efficiency far greater than any nuclear process. Much of this energy is radiated away as light across a wide range of frequencies, but some of it is channeled into jets. Relativistic jets are among the most powerful sustained energy releases in the universe, concentrated beams of plasma, energized particles, and electromagnetic fields launched from the poles of an accreting black hole and extended across distances that can exceed the size of the host galaxy by a factor of 10 or more. Galaxy M87, a giant elliptical galaxy in the Virgo cluster about 55 million light-years away, possesses a jet that has been observed stretching more than 5,000 light-years from the galactic center. The energy required to sustain such a structure over its lifetime is difficult to calculate and harder to believe. Jets interact with the surrounding medium, they heat the gas in the galaxy halo. They push material outward, sometimes faster than the galaxy's escape velocity. They can quench star formation across entire galaxies by heating the gas reservoirs that would otherwise collapse into new stars. A sufficiently powerful black hole at the center of a galaxy can, in this way, regulate its own food supply, heating the gas that might otherwise fall inward, reducing the accretion rate, reducing the jet power, allowing gas to cool again, and creating a feedback loop that keeps the system in a rough equilibrium. This is why the most massive galaxies in the universe do not continue forming stars indefinitely. The black holes at their centers eventually become powerful enough to suppress the process. Magnetic fields play a critical role in how all of this works, and observations of specific galaxies have allowed astronomers to measure just how important they are. Cygnus A is one of the most luminous radio sources in the sky outside our own galaxy, located roughly 600 million light-years away. At its center sits an active supermassive black hole driving powerful jets that extend across hundreds of thousands of light-years. When the magnetic field structure around this black hole was studied in detail, a strong and ordered magnetic field was identified in the innermost region near the black hole. The magnetic field serves several functions simultaneously. It threads the accretion disk, providing a mechanism for angular momentum to be transferred outward, allowing material to slowly spiral inward, while the magnetic field carries the angular momentum away. It channels material toward the event horizon in ways that purely gravitational infall would not produce. And in the immediate vicinity of the black hole, the interaction between the rotating black hole, the magnetic field lines threading through the event horizon, and the inflowing plasma creates the conditions that accelerate particles to relativistic speeds and launch them as jets. The difference between a galaxy with an active nucleus, blasting jets across its neighborhood, heating the surrounding gas, suppressing star formation, and a quiet galaxy like our own Milky Way, with its comparatively dormant central black hole, comes down in significant part to this: the presence or absence of sufficient magnetic flux threading the central object. The relationship between size and feeding rate is not simple. The most voracious accretors are not always the most massive black holes, and the speed at which a black hole can grow is limited. There is a theoretical maximum accretion rate for a black hole of a given mass called the Eddington limit. Beyond this rate, the radiation pressure from the material already falling in pushes outward strongly enough to halt further infall. The outward pressure of radiation balances the inward pull of gravity. Feed a black hole faster than this rate, a condition called super-Eddington accretion, and the physics of the inflow must change significantly. The standard thin accretion disk structure breaks down, material piles up, bloats, and the geometry changes. Approximately 12 billion light-years away, in the direction of the constellation Coma Berenices, there is a galaxy whose luminosity is extraordinary even by quasar standards. The source of that luminosity is a central black hole accreting at a rate that translates to roughly 100,000 kilometers per second of infall velocity for some of the approaching material. Spectroscopic analysis shows this material not orbiting the black hole in a stable disk, but moving radially inward, falling almost directly in with minimal rotational support. The gas has been characterized as nearly in free fall on a nearly straight trajectory toward the event horizon. This kind of extreme accretion, where material plunges nearly straight into a black hole rather than spiraling in gradually, may represent what happens when the accretion rate far exceeds the Eddington limit and the standard disk geometry collapses. The material simply falls in faster than the radiation can slow it. Sound in the conventional sense requires a medium pressure variations propagating through gas, liquid, or solid space. The popular understanding holds is silent, empty. Vacuum without a medium to carry pressure waves. The popular understanding is incomplete. The large-scale structure of the universe is not empty. The space between galaxies and between galaxy clusters contains diffuse plasma, hot, thin gas spread across vast volumes. in particularly dense environments, like the hot gas-filling galaxy clusters. This medium is dense enough and extensive enough to sustain the propagation of sound waves. Very low-frequency sound waves, waves with wavelengths of thousands of light years. At the center of the Perseus galaxy cluster, about 250 million light-years away, sits a supermassive black hole that has been pumping energy into the surrounding cluster gas for billions of years. The jets from this black hole drive expanding cavities in the cluster gas, bubbles of lower density pushed outward by the jet pressure. As these bubbles expand, they generate pressure waves, sound waves that propagate outward through the cluster gas in concentric rings, like the surface of a pond after a stone is thrown. The frequency of these sound waves was determined from the spacing of the pressure variations observed in X-ray imaging of the cluster. The result was a node approximately 57 octaves below middle C. The lowest frequency that a human ear can detect is around 20 Hz. The sound wave from the Perseus cluster completes one full oscillation in approximately 10 million years. These pressure variations spread hundreds of thousands of light years from the central black hole, gradually fading as the gas density drops between the Perseus cluster and Earth. The gas is too thin and too sparse to carry these waves. The sound is real, it propagates across an enormous volume of the cluster. But it arrives here as silence, not because it was never made, but because the medium through which it would have to travel has dissolved to near nothingness in the hundreds of millions of light years between the source and us. The lowest note ever recorded in the universe, generated by one of the universe's largest machines, unheard by anyone. The question of how massive a black hole can become is one of the most actively studied questions in modern astrophysics. The answer keeps getting revised upward. For most of the 20th century, black holes were known in two approximate categories: stellar mass black holes, formed from the collapse of individual massive stars, with masses ranging from a few times the mass of the Sun up to perhaps a few tenths of solar masses, and supermassive black holes, with masses ranging from millions to billions of solar masses, found at the centers of galaxies. The gap between these two populations was, for a long time, unexplained. The stellar mass category has since been extended. Gravitational wave observations have discovered black holes in the so-called mass gap, objects between roughly 50 and 100 solar masses whose origins remain under investigation. And at the other end, the upper limit for supermassive black holes has been repeatedly revised upward as observations of increasingly distant and massive objects have accumulated. The black hole at the center of our own galaxy, Sagittarius ARSS, has approximately 4.5 million solar masses. It is, in many respects, our reference point, the closest supermassive black hole we can study in detail. Its event horizon on angular scales from Earth spans roughly 50 microarcseconds. Its diameter is somewhat less than 20 times the distance between Earth and the Sun. 4.5 million solar masses sounds enormous. In the context of what we have since discovered, it is a middleweight. The most massive objects in the observable universe are found at the centers of the most massive galaxies, which are themselves found at the centers of the largest galaxy clusters. These are galaxy clusters that contain hundreds or thousands of individual galaxies, embedded in vast halos of dark matter, with their combined gravitational influence shaping the motion of galaxies across tens of millions of light years. In such environments, the central galaxy has typically absorbed dozens of smaller galaxies over billions of years. Its black hole has merged with dozens of smaller black holes. The result is a black hole of a scale that requires a moment to process. The quasar Arttom 618, located approximately 10.5 billion light-years from Earth in the constellation Canes Venatici, hosts a black hole with a mass of 66 billion solar masses. Its accretion disk, the ring of hot gas spiraling inward, generates emission lines whose widths indicate gas velocities of approximately 7,000 kilometers per second. The absolute luminosity of this object is more than 100 trillion times the luminosity of our Sun. The host galaxy is effectively invisible from Earth, drowned out by the light of its own nucleus. For perspective, a black hole of 66 billion solar masses has an event horizon with a radius of approximately 130 billion kilometers. That is roughly 20 times the distance from the Sun to Pluto, a volume of space comparable to a small solar system, but containing 66 billion times the mass of a star. And even this is not the largest candidate. In the constellation Cetus, approximately 700 million light-years from Earth, lies a galaxy cluster designated Abell 85. At the center of this cluster sits a galaxy known as Holmberg 15A, a supergiant elliptical galaxy, one of the most massive galaxies known to exist. Holmberg 15A was catalogued in 1937 by the Swedish astronomer Erik Holmberg. For most of the 20th century, it was noted for the unusual extent of its diffuse stellar envelope, the halo of stars surrounding the main body of the galaxy. It was large, it was massive, it did not attract extraordinary attention. Modern analysis has changed that assessment. The galaxy cluster Abell 85 shows a velocity dispersion in its dark matter halo of approximately 750 kilometers per second. This is the measure of how fast galaxies are moving within the cluster's gravitational potential, and it is extraordinarily high. The implication of such a velocity dispersion is a total cluster mass that only a central black hole of enormous size can help explain. Direct dynamical measurement, based on the motions of stars in the core of Holmberg 15A, produces an estimate of roughly 40 billion solar masses for the central black hole. This already places it among the largest known black holes in the universe. But the uncertainty ranges are wide, and some analysis based on the extended gamma-ray emission structure of the object and the kinematics of the stellar distribution push the estimate to 300 billion solar masses or beyond. If the higher estimates are correct, Holmberg 15A hosts a black hole whose mass exceeds 300 billion times the mass of our Sun. The structure of stellar orbits in the core of this galaxy provides an indirect but important clue about how it got this way. The distribution of orbital directions, whether stars tend to orbit in elongated ellipses aligned radially toward the center, or in more circular paths aligned tangentially, is different in Holmberg 15A from what is seen in most other elliptical galaxies. The pattern is consistent with what is predicted to result from a specific kind of event: the merger of two supermassive black holes in the recent galactic past. When two supermassive black holes merge, they eject stars from the core through gravitational slingshot interactions, preferentially removing stars on certain kinds of orbits and creating a core, a region of lower than expected stellar density. The shape of this core and the distribution of orbits within it carries a signature of the merger history. Holmberg 15A's core matches that signature. The object at its center is not the result of a single formation event. It is the product of an accumulated history of mergers, galaxy eating galaxy, black hole absorbing black hole across billions of years of cosmic history. The endpoint of that process, at least as far as current observations can determine, is an object whose gravitational sphere of influence extends hundreds of light years in every direction, whose event horizon spans a volume comparable in size to a significant fraction of our solar system, and whose mass, in the conservative estimate, approaches 40 times the mass of 2 on 618, to feed a black hole of this scale at a rate comparable to the one at the center of the Milky Way, it would need to consume the equivalent of 2/3 of all the stars in the Milky Way, simply to match the proportional accretion rate. It does not need to, because Holmberg 15A is not feeding at that rate. But the scale of the comparison puts into perspective how different these objects are from anything in our immediate cosmic neighborhood. In April 2019, the Event Horizon Telescope collaboration, an Earth-spanning array of radio telescopes functioning as a single instrument with an effective diameter equal to the diameter of the Earth, released the first image ever obtained of a black hole's event horizon. The target was the supermassive black hole at the center of galaxy M87, 55 million light-years away. The image showed a ring of bright emission, the photon ring, the region where light orbits the black hole on nearly circular paths before either escaping outward or falling inward, surrounding a dark central region, the shadow of the event horizon. 2 years later, the same collaboration published polarized light images of the same object. Polarization is the orientation of the oscillation of light waves. In the environment near a black hole, the magnetic field controls the motion of charged particles, and those particles emit radiation whose polarization is aligned with the field geometry. By mapping the polarization pattern across the photon ring, the team was able to map the structure of the magnetic field at the edge of the event horizon, in the exact region where the jet, extending 5,000 light-years from the nucleus, is being launched. The magnetic field there is ordered, it is strong, it is structured in a way that is consistent with theoretical models of how jets form, models in which the rotation of the black hole, combined with magnetic field lines threading through the event horizon, acts as an electromagnetic engine converting rotational energy into outflowing plasma. The image confirmed what equations had predicted for decades. But seeing it measuring the actual field lines in the actual region around an actual black hole was categorically different from solving a differential equation. The abstraction became a measurement. The theory became a map. We are at the beginning of this kind of direct observation. The Event Horizon Telescope continues to develop. Future arrays may achieve sufficient resolution to observe the shadow of Sagittarius A in our own galaxy in real-time detail, to watch the accretion disk structure change, to track individual blobs of plasma as they spiral inward and disappear below the horizon, to literally watch matter cross the point of no return. Black holes were once thought to be perfect sinks, objects into which things disappear without remainder. Stephen Hawking's 1974 calculation changed that picture. By combining general relativity with quantum mechanics at the event horizon, he showed that black holes should slowly emit thermal radiation, a process now called Hawking radiation, and that this emission over incomprehensible timescales should cause them to slowly lose mass and eventually evaporate. The temperature of this radiation is inversely proportional to the mass of the black hole. For a black hole of stellar mass, the Hawking temperature is a fraction of a billionth of a Kelvin, colder than the cosmic microwave background, meaning the black hole absorbs more radiation from the universe than it emits. It grows, not shrinks. Only when the universe cools further than it currently is far in the future, far beyond any human timescale, will stellar mass black holes begin to evaporate. And for supermassive black holes, the time scale for complete evaporation is longer than the current age of the universe by a factor that contains more zeros than this sentence can hold. This raises what is known as the information paradox. If a black hole evaporates and disappears, what happened to the information, the complete quantum state of everything that fell in? Hawking radiation, as originally calculated, is purely thermal, random. It carries no information about what fell into the black hole. If the information is truly gone, this violates a fundamental principle of quantum mechanics. If the information is somehow encoded in the radiation, the mechanism by which this happens is not understood. This is not a solved problem. It is one of the central open questions of theoretical physics. The contradiction between what general relativity says happens at the event horizon and what quantum mechanics says must happen to information is the fault line along which a theory of quantum gravity, the as yet undiscovered framework that will unify both pillars of modern physics, will need to be built. Black holes are not just the largest, most extreme objects in the universe. They are the location where our understanding of nature is most visibly incomplete. Every observation we make of them, every image, every gravitational wave signal, every spectroscopic measurement is both an answer and a question, a confirmation of how far the current theory reaches and a pointer toward where it breaks. The mathematics predicts infinities. The observations find finite, measurable things. Somewhere between the two, in the gap between what our equations describe and what the universe actually does, lies the physics we have not yet discovered. And that gap is exactly where the next discoveries will come from.